In this lesson, we will be talking about the slope of a straight line. I don't want to call it a curve. We usually do that without thinking about it, but and when someone starts to argue with the curvature of a straight line, and then we start to have some issues. So for us, I'm just gonna say that I want us to talk about the slope of a straight line or a linear function or just a linear function. Now, I wanted to draw two plots here. One plot is going this way, and this point here, I want to say that this point is maybe 1, and then this point here, I'm just going to say it is -1, and then this point here, I'm also going to have another curve here, and then, okay, let me just see, I also have another function here, which is going all the way to negative infinity, all the way to positive infinity. And then this is y, this is x, and this is some constant. It can be 5, it can be 7, it can be anything. So these are x's, these are y-axis. I also wanted to do another final plot somewhere here, and then we talk about these plots. Gonna plot something here. We'll try and make sure that we don't end up losing time unnecessarily. And then here I'm gonna have another plot, and then this one here, I want it to be different than the previous ones, to be something like this. So, and this one, let me just say this is our f. Of course, this one also is our f. Of course, this one is also our f. Right. Now, what is a slope of this straight line? The slope of a straight line, we usually denote it by m, and it is actually the change, the ratio of the change along the y-axis divided by the change along the x-axis. That's what we mean by a slope of a straight line. So here, if you want the slope of this straight line, you just need to find 2 points. I can find any point maybe somewhere, but here I would like to say this is going to be my x2, this one is going to be my x1, so that I can say that this is always gonna be y2 minus y1 divided by x2 minus x1. This is the slope of this particular function here, linear function. Now, if this slope is bigger than 0, if I plug in the numbers here and I get a number that is bigger than 0, it means this function is increasing. If this slope is actually equal to 0, when I'm plugging in the numbers, I end up getting a 0. It means that this function is not increasing, it is not decreasing, it is a constant function, so it's not increasing. And if it happens that this is negative, then it means that this function actually is decreasing. So that is the slope in general. So if, let's say now this function is f of x, then to get a y2, we're gonna take this x2 and plug in f of x, and you end up having f of x2 minus, and then to get y1, you get you take f of x1 or x1, you plug it in f of x, and you divide this by x2 minus x1. So this is one way of actually writing the slope of the function f. And now let's look, let's take an example here. You can see that this coordinate here, x is equal to 0. So this coordinate x is equal to 0 and y is equal to 1. And in this point here, you can see x is equal to -1 and y is equal to 0, because along this axis, you will get this y is equal to 0 along the x-axis. Now, If we wanted to find the slope of the first function here, we'll actually look at these points. You have to make sure that you mark them. If this one is your x1, this must be your y1. If this one is your x2, this must be your y2. And then y2 minus y1 is going to be 1 minus 0. So we'll end up having 1 minus 0 divided by, and then you come here again, you look at this was x2, so you're going to have 0 minus 1. So we'll end up having 0 minus 1, and this is just 1 minus 0 is 1, and then 0 minus 1 is just 0 plus 1, which is 1 over 1, which is equal to 1. This is greater than 0, which means the function is increasing. But if we take a look into this example here, you will find out that if I pick my x1 to be here, then when you are going all the way up, you will find out that our y1 is just equal to this constant c, because this is a straight line. So we have c, y1 is equal to c. If I pick my x2 to be here, this is my x2, I go all the way up to this curve, I will get my y2 equal to c, and then the slope of this function is going to be y2 minus y1 all over x2 minus x1, which is going to be our y2 is c, our y1 is c, all divided by x2 minus x1, which is the same as 0 over the difference in x, which is just 0. So this one is a constant function, and the slope is always 0 when the function is not changing or is constant. Now, I want us to talk about how can you say, if I pick a point, let's say I pick a point here, and down there I'm calling x1, and then here I am calling, this is going to be x2. Now, how can you tell if this function, you can see that this function is going this way, going this way, going that way, and you want to know, suppose that this function was actually representing my investment, for instance, and if that is a particular case, I want to know if is my investment actually growing or is it decreasing. So that's also what I want to find out, if this is actually representing an investment. So if I place a line here, a straight line that passes through these 2 points, and then this I'm calling it G. It passes through that point, it passes through that point. The slope of this line, which passes through these 2 points, will actually tell us if this slope of this line is bigger than 1, it says that this straight line actually, which represents G, is actually an increasing function if the slope is greater than 0. If it is less than 0, which means this function is actually decreasing. Now, looking at this, I just want to say, let me just say this part here is just the arc. If this slope here is saying that this function is increasing, it means that between this point and that point, this function f is increasing on average. That is why we usually say that m is equal to change in y divided by change in x. We usually call this the average rate of change. It is an average rate of change of y with respect to x. So it comes from the fact that if I were to pick 2 points and I want to find out if this function is increasing or decreasing, on average, by placing a line here, then I will be able to know that actually this function is increasing on average or it is decreasing on average. And also, if let's say you have a function that is going this way and then it's going that way and then it's going that way, so for those who likes, let's say, trading, you'll find out that trading usually goes in this particular fashion, and you place a trade here. when you are looking at this point and that point, you can see that actually there is a decrease. But if I pick a point maybe somewhere and then I place a line that is going to pass through that, you can see that your money is increasing on average. So this is the average rate of change of y with respect to x. Or we can say this is average, or we can say it is a slope of that particular straight line, or you can just say it is a gradient. Now, if let's say I am giving you a random curve, this is a random curve, I'm gonna call it f, and then there is a point there which is an output of x1, and there is a point there which is an output of x2, and the difference between x and x2 is change in x, which means that to get x2, I just have to say x1 plus the change in x, then I will be able to get x2. And if I wanted to find out, given that this function is f of x, at this point here, I take this x value, I plug it in that function to get the output here, or the value here. So this point here is going to be f of x1. And then this point here, I'm going to take x2 and then plug it in f of x. So I will end up having f of x2. And then if I place a line to pass through these 2 points, the slope of that line, or the average rate of change of this particular function f of x between these 2 points, is going to be given as f of it's going to be y2 minus y1 divided by x2 minus x1. This is going to be the same as you're gonna end up having f of x2 minus f of x1, right? Because this is x1 and the output that is associated with that, and this is x2, the output associated with that is that. And then you divide what is inside is going to be x2 minus what is inside, which is x1. If you decide to switch these around and you want to say y1 minus y2, we also switch this one around because we want x2 and x2 to be matched and x1 and x1 to be matched. Now, taking a look into this phenomenon here, or this scenario here, knowing that the change in x is actually delta, is actually x1. I mean, the change in x, we know that the change in x is always going to be x2 minus x1. So to get your x2, you're always going to say it's going to be x1 plus delta. Right. Now, let's deal with this thing once and for all. The delta here, to get this difference, I have traveled from this point to that point, and now there is also this little travel. So if I have gone up to here, I want to find out here this value here. I'm just gonna say this point which start from the origin up to here minus this little point, I will get this remainder there. Hence we have that part there, and by just taking this to the other side, I end up having that. So that is why this formula is always gonna be, instead of x2, we just use x1 plus delta x minus f of x1, right? The reason for that, we're using this because sometimes you're given delta, sometimes you're given the points. If you are given the points, you can use that equation. If you are given the function, you can use that. But if you are given delta and 1 point, you must know that x2 minus x1 is just gonna be delta, and here this is an initial point plus delta, this is the initial point and then delta. So this formula is usually useful when you are given delta. Now, why do we spend so much time with this average rate of change of this straight lines? Is because if you are given let's say a function like this, we will want to create this function by just having some slopes, creating it with some straight lines of this particular sort. So once we know the gradient of these lines, we can actually create this whole function with these likely slopes here. Now, Can we actually take the examples that is actually the examples that are actually gonna tell us more about this average rate of change? And in most cases, you will always find out that instead of placing a delta here, delta x is always gonna be there, and then delta y is actually that side. But that's how this usually thing is actually done. Now let's take some examples here. The first example is saying, given the function f of x is equal to x cubed minus 6x squared plus 9x plus 4, find the average rate of change of the function on the interval. So we have some function, we don't know how to plot it, but one thing that we know of is that whenever you have your x1 equal to 1 and your x2 equal to 4, one thing for sure is that the line that the outputs will be in the function, and also the line that is passing through will actually help us. Now whenever you have these square brackets here, remember that in this interval x includes this and also x includes that. These values are not saying that you have a coordinate. This is not a coordinate, it is an interval. This is x1, this is x2. Now how do we end up finding the average rate of change? Of course, the average rate of change we say is m, and it's always gonna be change along the y divided by change along the x. And of course, in this particular case here, we are given f, so we wanted to have f of x2 minus f of x1 all over x2 minus x1. And then what is our x2 in this case? We know our x2 is going to be 4 and our x1 is going to be a 1, which is that. And then x2 here, if I replace that, I will have f of 4 minus f of 1, because this one's supposed to go inside there. The next thing that I need to find f of 4. So I'm going to take f of 4 and plug it inside this equation and see what I am going to get. So I will have 4 to the power 3 minus 6, 4 raised squared plus a 9 times a 4 plus a 4. This is equal to, of course, you can either press your calculator here if you have one. If you don't have one, you can always try and work this thing out. Because of time, I'm not gonna be doing that. This video will end up being so many hours, and then we're gonna have plus 9 times 4, and then we have a plus 4 here. The answer is 8 here, so we have an 8. And then now we check what is f of 1. F of 1, I'm going to plug in 1 here. We'll have 1 cube minus 6 times 1 squared plus 9 times 1 plus a 4, which is equal to, of course, you can do the same thing here. You have 1 cube, and then you have minus 6 times 1, and then you have plus 9 times 1, and then you have plus a 4. So this is also 8. What does that actually mean for us? It actually means that I have some space here. It means that now our m, which is equal to delta y divided by delta x, is supposed to be equal to this value here is 8 minus 8 all over, because f4 is 8 and this one is 8. And then we divide that by 4 minus 1, which is just equal to, here you have a 3 and then you have a 0. 0 divided by 3 is a 0, which means that between this point x in this interval where we're starting here and there, this function here on average is not increasing at all, which means it is there's no increase or decrease there. It is still at the same values. And then now we are done with the average rate of change. Let's go to example number 2. Example number 2 is saying a car's position as t in meters after t seconds is given by this particular equation here. Find the car's average velocity between t is equal to 2 and t is equal to 5. Okay, let's talk about this for a moment. They are saying find the average velocity. Okay, now you are given position. Now if you take the final position and then you subtract the initial position, you divide by the change in time, what you're gonna get, you will end up getting the velocity. Instead of just saying find the rate of change, they just decide to say average velocity, which is the same thing in this case, because this is position. When you're dividing a position by time, you end up getting a nice velocity. So here the average velocity, you can say that in this particular case, the average velocity, we're just gonna say some v here is going to be, as others they say, average, or we can just use the m as usual. Average velocity is going to be m is equal to the change, because here we have st, so I'm just gonna place the y as we used to, and then here I'm gonna place s of this is y2 minus y1 all over x2 minus x2. Of course, our y2 is going to be s of x2, because I have to take x2 and plug it in this function, get y2, minus s of, I'm going to take, this is supposed to be x1, I'm going to take x1 and plug it inside here to get the first output. So I'm going to have x1 here all over x2 minus x1. Now, in this case here, if you look carefully, you will find out that our x2, remember that x2 is supposed to be the biggest time there is, so it's supposed to be t is equal to 5. So we're going to have a 5 minus, and then our x1 is going to be a 2, and then inside here, I will have s of 5 minus s of 2. Of course, you go to the function here and plug in and see what you are getting. So first of all, I want us to find s of 5. So wherever I find t, I'm going to place in a 5. So I'm going there. I will have 5 times 5 squared, and then minus 2 times 5, and then plus a 3. I will get an answer. My answer should be 5 times 5, and then I'm going to square that up, and then I'm going to say minus 2 times 5, and then I will add a 3. So I have that, just to double check, 5 and 5, and then we have a minus 2, 5, and then we have a 3. The answer is 118. So we have 118. And then if you look now for s of 2, you will find out here 5 times 2 squared minus 2 times 2 plus a 3. The answer will be 4 times 5 is 20. 20 minus 4 is 16 plus 3 is 19. But let me check, double check here. So here I'll have a 2, and then that side I am going to also have another 2, and then the answer is a 19. So I have a 19 here. Now, what are we going to get here? This simply means that this whole thing is going to be 118 minus 19 all over 5 minus 2 is just a 3, and then I can go in here and say actually this is going to be 99. Yes. Okay, let me just say minus 118. Yeah, it's going to be 99 divided by 3. And of course, how many 3s out of 9? We have 3. And how many 3s out of 9? We have 3. So we're supposed to have 33. Of course, I can double check there by dividing by 3. So I have a 33. So that's actually the average velocity. Of course, you can just say meters per second, because average velocity have these units. But what is important here is just the number. Now, let's consider the function. You are given this function here. This function is a piecewise function, whereby this function is equal to x squared if x is less than 2. and this function is equal to 4x minus 3 if x is greater than a 2. The question is, find the average rate of change of f of x on the interval. Again, this is interval along the x-axis such that this one is going to be your x1 and this one is going to be your x2. So here you need to find the average rate of change, your m, which is equal to change in y divided by change in x, which is just equal to y2 minus y1 all over x2 minus x1. Of course, if you look at y1, we don't have any y1 here. We have f of x, so y2 is going to be f of x2 minus f of x1 just for this part, and then you divide this by x2 minus x1. Now we try in and punch in the numbers. Now before we go in, let's first find out f of x2. And if you look at x2, our x2 is 4, so we want to find out what is f of 4. So 4, you come here, is 4 less than or equal to minus 2? That's a big no. 4 is greater than 2, therefore we are coming for this equation. So f of 4 is going to be 4 times 4 minus a 3, which is equal to this is 16 minus a 3 is supposed to be 13. Just to double check, 4 times 4 minus a 3, you have a 13. And then if we are looking for f of x1, f of x1 is the same as f of this is a 1, so I'm going to place a 1 there. And then this 1 here is the value of x. Is x bigger than 2? Is 1 bigger than 2? That's a big no. So 1 is actually less than 2, so we are using that equation there. So we'll end up having 1 squared, which is the same as 1. And then we go forward and we say that our m, which is equal to delta y divided by delta x, is equal to, in the value of this, I'm going to place a 13 minus, in the value of f1, I'm going to place a 1, and then the delta here is supposed to be 4, x2 is 4, and then x1 is 1, and then 13 minus 1, that's a big 12, and then here we have a 3. The answer we're looking for here is supposed to be a 4. So for this one, you can see 4 is bigger than a 0, therefore this function is actually increasing on average on this interval. And now let's look at another example here. Let h of x equal to x squared plus 4. Let x be equal to that. Compute the average rate of change of h of x on the interval 2 to 6 and interpret the results geometrically. So first of all, I want us to note that we are given the interval from x1 up to x2. So these are not the coordinates, it's just the interval. We are given a function. And actually, we are looking for m, which is equal to delta y divided by delta x. Of course, delta y is y2 minus y1 all over x2 minus x2. X2 minus x1. And then if you work your magic around this, you will find out that we are looking for h of x2 minus h of x1. And then you divide this by x2 minus x1. And then of course, once you are here, we already know that this one here, which is a 2, is going to be x1, and then a 6 is going to be x2. And then we actually start looking for we're looking for h of x2, which is the same as h of 6, because x2 here is actually 6. So I'm going to plug in 6 wherever I see an x there. So this is supposed to be the square root of 6 squared plus a 4. I'm just gonna punch in the calculator here to save time. So we're gonna have 36 plus a 4, and then we're gonna have this is equal to 2 root 10. And then if we are looking at h of x1, you will find out that we have h of 2, because we're starting at 2, so x1 is 2, and then I'm gonna have this nice thing here, and then instead of x I'm gonna plug in a 2, so I'll have a 2 to the power 2 plus a 4, which is equal to, there is a calculator there, the square root, you're gonna have 2 squared, and then you have a plus 4, so this is going to be 2 root 2. So you have that nice those nice calculations there, and then our m, which is the delta y divided by delta x, is just equal to this part here. We said that it is 2 root 10 minus this part here, we said that it is 2 root 2, and then you divide that by what was our x2. X2 was 6 and x1 was a 2. So here you will find out that 2 and 2 is common. I can take it out, and then I will have square root of 10 minus square root 2, and then all over 6 minus 2 is 4. 4 is the same as 2 times 2. So if you work your magic around this, you will find out that how many 2's out of 2 is 1, so this one is gone. 2 out of 4, we have 2 of them, so we end up having square root 10 minus square root 2 all over a 2. So we have a 2 here. We have a 2. There's nothing that can be done here. We can leave this as it is, or you can punch in the calculator there and say, I want to find an approximation of square root 10 and then minus square root 2 divided by not a 4, a 2. The answer you will get is the same thing. There's nothing, but if you want to approximate it, is 0, something something, which means this function is actually increasing, right? So interpret the results geometrically. So what does that supposed to mean? Let me just say this is approximately 0.874. I'm just gonna have that. What does this actually mean? It means that if this graph here, you had drawn a graph like this, and then you pick these points here, on that interval, this curve here is actually increasing on average. So this curve here between this, or in this interval, it is increasing on that interval. Or you can say that the arc of this curve on this particular interval, it is increasing, or that second here, you can say it is increasing on this particular interval because this one is actually positive. Another example would be the table below shows the values of a function at different points. So we have x when x is equal to 1, f of x is equal to 5, when x is equal to 2, f of x is equal to 8, and when x is equal to 4, f of x is equal to 14. The question is, find the average rate of change of f of x from x is equal to 1 to x is equal to 4. Now, what this actually means, this means that this is supposed to be your x1, this is supposed to be your x2, because it's saying the average rate of change from this to that. So how do we find it? It's very simple. Your average rate is going to be a change in y divided by change in x, which is the same as y2 minus y1 all over x2 minus x1. And in this particular case here, when I'm going for x2, for y2, what is the y value, or f of x corresponding to 4? I will go here and say it's 14, so I will pick a 14, and then 14 goes with 4, I will have a 4 here, and then minus minus, and then I come here with y1 that correspond with x1. x1 is 1, so I will have a 1 here, and then this side I will have a 5. So the output is 5, the input is actually 1. So here 14 minus 5 is supposed to be a 9 divided by 3, so the answer here is just supposed to be a 3. So the average rate of change from x1 to x4 is just a 3. Another example would be the temperature T of H in degrees Celsius at different hours H of the day is recorded below. You have 6 hours, this is the temperature, and then if we after 12, you have this after 12 hours, you have this, and then after 18 hours you have that. Estimate the average rate of change of temperature from 6 a.m. to 12. So here I want my x1 to be equal to 6, right? Because 6 a.m. it means that we're still at 6 hours. And then if I have this, then my y1 would be equal to the output there, which is 15 degrees. And then my x2 is the final output here, which is actually 12 p.m. to 12 p.m. 12 is somewhere there, so this is going to be 12, and then my y2 is going to be 25. Then the average rate of change, let me not just write here, let me open a little bit of space. The average rate of change here, m, is going to be the change. We can always use y, or because this is t, you can just say the change in t divided by change in small letter t. So this one is the change in time, this one is the change in temperature. You can use that or use our original data y, data x is still fine. These are dumb variables. So when it comes to this, you will end up having your y2, and then you're gonna have, this is going to be x, you're gonna have your y2 minus y1 divided by x2 minus x1, and then y2 we said it is 25, and then minus, and then y1 we said it is 15, and then we divide that by 12 minus 6. Of course here 25, we have 25 minus 15 is supposed to be a 10, and then 12 minus 6 is supposed to be a 6. Also, the common factor here is a 2. How many 2's out of 10 is supposed to be 5, and how many 2's out of 6 is supposed to be 3. They said estimate, so estimate, they are looking for an approximation. So an approximation of this is going to be how many 3's out of 5 will end up having 1 3, and then we have a remainder, the remainder is 2, and then how many 3's out of 2, there is no 3 out of 2. You place a comma. When you're placing a comma, you add a 0. You ask yourself how many 3's out of 20. You will find out that actually you have 6 of them, and then the remainder is still 2. And then you ask now how many 3's out of 2, they don't go, and you add a 0. And then how many 3's out of 20, you'll find out that you have 6 of them, and then the remainder is 2. So we'll end up having 6, 6, 6, 6, 6, 6, 6, 6, and it goes all the way. You have this 6 here. This one here, if I were to go like this, it's actually not an approximation, it's an actual value. But if I were to approximate it into 2 decimal places, it's going to be 1.67. Now, this is going to be, I'm just going to say it's going to be degrees Celsius. I can just put it this one here, degrees Celsius, because we are dividing by time, and time was in hours per hour, right? So this is what was going to happen. Of course, we can always check this. What is 10 divided by 6, just to make sure that we made the right truth. So we have something like that. Yeah, so actually it's not that bad now. And this one is positive, which means that there was an increase in temperature. And then now when you're actually moving from 12 to 6 p.m., we're gonna have 18. So in this case now, our x2 is going to be 18 hours, and then our y2 is going to be 20 degrees Celsius, and then our x1 is going to be 12 hours, and then our y1 is actually going to be 25. So that's what is actually happening in this particular table, because now from 12, so we use this point and that point. 6 p.m. is the same as 18 hours. So this is going to be y2, this is going to be y2, this is going to be x2, this one is going to be x1, and this is going to be y1. And now, of course, what we will actually end up with here, we will end up having our average gradient as y2 minus y1 divided by x2 minus x1. And of course, when you're punching in the numbers, you will end up having 20 minus 25 all over 18 minus 12. And then here, the difference is going to be minus 5, and then you divide here by the difference, of course, is 6. So if you look into this, you can say that you have minus 5, and then you divide that by 6, and then you will say that you have this is approximately equal to minus 0.83. This little bar here is saying this tree continues, but now because I'm approximating it, it's like that. We have a little negative here which says that there was a decrease or a drop in temperature. As you can see, we had 25 and then it dropped to 20, so there was a significant drop. Now, our last exercise now is this. If a stone is dropped from rest and allowed to fall under the influence of gravity only, so we have this stone, we were carrying a stone somewhere, and here this was a stone, right? Now we have this stone, we just let it go from rest. In other words, here the speed was 0, so the speed here, it was 0 meters per second, so we just let it go. And we are also assuming that there is no air resistance there, because if there is air resistance when an object is going this way, air resistance is actually pushing the object to go that way. And if the object is going that way, air resistance is trying to push the object to go that way. So we are assuming that we don't have that air resistance, or that friction that is caused by that opposite force that is caused by air resistance is not there. We only have force of gravity that is actually pulling. We only have this gravitational force that is pulling this stone here. Then it can be shown that the distance st can be given by this, right? When if we would track how long has fallen, we can actually track it like this, with this equation here, where g is a constant and it's usually called gravitational acceleration, and it is equal to 9.8 if we are using meters, kilograms, second system. But if we are using feet, pound, second, it is 32 feet per second squared. So the question now is, you already have this equation, calculate the average rate of change. The average rate of change, and it's given like this, whereby the change in time is 1 second and the initial time is t is equal to 1. How can we actually find the change in position? So the change in position here with respect to data time, of course, now because we are given the change and the initial time, right? All we need to realize here is that we will end up having s of initial time, which is given, plus the change in time, minus s of initial time that was given, divided by the change. So we use this formula here if we're actually given this, as we said earlier on. Now, if I take this, let me just work this one out. As the initial time is given as 1 second, the change in time is given as 1 second, minus s of initial time is 1, and then the change is 1. So this is going to be s of 2 minus s of 1. Take note that 1 divided by 1 is not going to bring any difference here. Now, we want to find out what is s of 2. Now, s of 2 is not that hard from that equation. We have 1 over 2 times g, and then we have a 2 squared minus 1 over 2g times 1, and then the final answer will go smoothly and say we have 1 over 2 times g times 4 minus 1 over 2g. So this 4, I'm just going to place it as a numerator there, so we will end up having 4g over 2 minus g over 2. And of course, if you look into this 4, we have a 2 and a 2, so I can have only 1 2, and then I'll have a 4 minus a g, 4g minus 1g, which is the same as 3g divided by 2. And now, if you look carefully on this, if I take 3, I divide it by 2, and then I multiply this by 9.8. We get some interesting results here, which is equal to 14.7 meters. Remember that this one is in seconds, and then when you are having this time here, so it's going to be 15 meters per second. So we end up having this nice thing here. Let's go back. This is time, this is position. So of course what we'll get is in meters per second, which is one of the expected answers for those who have done physics. It's supposed to be of this kind. Another thing that you have to restrain yourself from doing, if let's say this is the position, right, and you decide that I am going to take the first derivative of this and get, if I multiply this, I'll end up getting g times t. And then you plug in a 1 here, which is this initial position. What you will end up getting here is actually you will end up getting g times 1, which is just equal to 9.8 meters per second. Right. Now, 9.8. What is the difference between this, just taking the first derivative, and actually taking this average? Why are these two different? Now, remember that the first derivative, it is the speed at this particular point. So that's the actual speed at this point. When t, after 1 second, this will be the speed of that stone if there is no air resistance. That's the meaning of this. But average, this average here is not the speed. It is the average speed between this point t is equal to 1 and t is equal to 2 seconds. That's the average speed between those 2 points. Remember, if we are talking about an average, if I were to draw a curve here, and my curve is like this, it can drop, it can go up, it can go down. If the initial point is here and the other point is there, the average passes through these points. It's not actually the speed at this point or the speed at that point. It is actually the average. How is this thing? How is the average of these speeds in this particular interval? So it's the average, not the actual speed. So here we have an average, and then here we have the exact speed at t is equal to 1 second. That's the difference. Yes, I think that will be the end of this. Next time we will be actually talking about what is the slope of the tangent line that is touching the curve at one point. I think that's actually going to be one of the